Okay. Perfect. So then, yeah, I'm Markus Fleischauer. I'm a postdoc in Sebastian Böcker's group, and together with my colleague Fleming, we will guide you to the Sirius part of this workshop. And Sirius is basically all about annotating metabolites from LC-MS data. And Sirius is not only a software, it's also a tool in our software, because Sirius is more or less a toolbox of different tools that will provide you different annotations for your MS data. As input, we can either use preprocessed data, as we will, can you see my pointer? No, okay. We will either use preprocessed data, as we will do in this workshop. So you will use your data you have preprocessed with NTMSS2023, and we will use it at input, but it's in general also possible to like do directly use the MZML files and do the alignment within Sirius. So yeah, I will like guide you through 3, maybe 4 different tools, which are Sirius for molecular formula annotation, CSI FingerID for searching in a structured database, and Canopus for compound class annotation. And if we have some time left, I might make a few comments on Zodiac. There are also other tools in Sirius, for example, Agordo for lipid class annotation, but we will not cover that here. And there's also Epimetheus for annotating the peaks in your spectrum to substructures. But this is only like for visualization and validation, and so Fleming will cover that in the live part, in the live demo of this workshop. Yeah, and we already have talked a lot about spectral library search for annotation, so you know very well what that does. You take your spectrum, searches in the spectral library to get a structure hit back. With Sirius, we now want to go one step further. We basically want to provide you additional in silico annotations by searching your spectrum in a molecular structure database. These are like much bigger than spectral libraries, because obviously not for every compound we know, we also have a reference spectrum. And so this really gives us the possibility to search against the entire chemical space we know. However, how do we match spectra against structured databases? So because like structures and spectra do not look very similar, so we have to do some steps in between. And here's a short overview about the tools and the steps you can do to get to your structured database search result. And we will now start with the first type of annotation Sirius can provide you, which is basically the molecular formula of an MS spectrum. Yeah, so as I said, it's not only the software, it's also the method for molecular formula annotation, just to be a bit more confusing. And in the upper left of the slide, you see a tag that says de novo. I have this tag on every like method or step that works de novo, and de novo basically means that we do not search in the database at all. So we directly derive the results from the data, and so this allows you basically to get annotations for all of your features, and you will not have the problem that like you will not have a hit in the database, because simply there is no database. But now let's talk about molecular formulas. So the first thing we usually do is we try to get candidates, so possible molecular formulas. And Sirius is like not taking them from a database, but it rather creates all possible molecular formulas that are theoretical possible for a given mass. So we will basically generate a list of all possible formulas, and we take like the precursor mass and like some given mass accuracy and generate all possible formulas. So for smaller compounds, this might be a few hundred or it might be a few thousand, but for like high mass compounds, that really can be millions. Nevertheless, it usually is quite fast. However, for very, very large compounds, there might be like a bottleneck, and we like have to apply some thresholds to not like have to do the whole downstream analysis for each of these candidates. However, just candidates, and even millions of them are not very helpful. So we somehow have to decide which of them fits best to our data. We have two sources of information we use for that. One is the isotope pattern from the MS1 spectrum. So what Sirius does here, it takes the molecular formula. So for each of these candidates, it simulates the isotope pattern and compares it to the measured one in your in your MS1 spectrum. This then gives us a score we can use for ranking. I will not go in detail with this method. And the second method we use is basically the fragmentation trees. So this is like some representation of your fragmentation process. It's not the truth. It's really just like to structure the data in a like more informative way. So this must not be the true fragmentation process, but at least it's like some good interpretation. Yeah, the good thing is both of these methods give us log probabilities as scores, which just means you can sum them up and have a combined score that makes sense. So we don't have to think about that. But yeah, now let's explain this fragmentation tree a bit more. So as you see, this is we have like our spectrum and our precursor mass, and usually we now, as I explained, generate this list of molecular formulas. And for each of these possible molecular formulas, we now try to find a fragmentation tree, because like this fragmentation tree gives us a score for ranking the molecular formulas. So for every tree, we start with this precursor formula, with this quotative precursor formula, and put it like at the top of this graph-like structure. So as you may see in the spectrum at the left side, we like have color-coded the peaks in correspondence to the graph you can see here. And we have only one node at the top of this graph, and we have several nodes for each fragment below this node. We have several nodes for that, because like for each of the fragment peaks, we now can again do this mass decomposition. So we can again generate all possible molecular formulas. Doing so, we have just one restriction for that molecular formula. It needs to be a subformula of the precursor formula, right? Because like we cannot just magically generate additional elements or something like that. So and then we are like have some scoring function that we have learned from the data that we apply to basically find the best possible tree. And the most important part of this scoring is basically that we have statistics about common neutral losses. So we basically have scorings that take into account how common is a specific loss between a molecular formula and like a fragment formula that is connected to it, right? So the nodes are like fragments that match peaks, and the edges are basically the common losses that are have to like get lost during the fragmentation process. So then we basically can like do the optimization, find the tree that explains the spectrum best, and we do this basically for each of the precursor formulas. So we will like get a battery of trees, and each of these trees gives us a score. This score we can then again use to rank the precursor formula. And that's basically the whole method behind identifying a molecular formula de novo from MS data. And here's like just some brief evaluation. So we are like the currently implemented version uses the top green method, which we have since Series 4, and since then this has not changed much. And you see, you will get almost like 90% of the formulas in the top 2. So, okay, now we have the molecular formula, and we have generated this data structure, this fragmentation tree. So this means we have now at least some information, and we have better structured our information. And so we now can go to the next step. So you might already see these methods depend on each other. So the structured database search needs the fragmentation tree and the molecular formula as input. So that means we can now do CSI FingerID, which enables us to search our spectrum in a structured database, but we cannot do this directly. Before we can search in a database, we make use of some structure representation that is much easier to compare than like structures, right? So structures are these 2D-like, graph-like things, and these are super hard to compare. And so we try to transform this into like a one-dimensional representation. And for that, we use molecular fingerprints. So we have not like invented them. They have been there before. They are used for comparing molecular structures since a long time already. And who of you knows already what a molecular fingerprint is? Okay, quite a few, perfect. So a molecular fingerprint, I will then shortly explain it, is basically, we have this vector, and each position in the vector basically like represents a substructure or functional group or something like that. And then for a given molecule, we can just look into the molecule, and like for each position, we decide, is this substructure part of the molecule? If yes, we say 1, and if no, we say 0, and then we basically get this representation of our molecule. So that means for our database, for our structured database, it's easy like to compute this fingerprint. But how do we get this fingerprint from our spectrum? And that is basically the task CSI FingerID does. So it takes the fragmentation tree and the molecular formula and the spectrum and predicts a molecular fingerprint. And you might have noticed we do not have zeros and ones here anymore, because now for each position we do not like know for sure if it's in there or not, but we rather have a probability. So if there is an 0.9, the predictor says, okay, I'm super sure it has to be in there. If there is an 0.1, the predictor says, okay, I'm super sure it's not in there. And if there is a 0.5, the predictor says, I have no clue if it's in there. This is basically what we will then use in a few secs for the structured database search. And if you look in the upper left of my slide, we are still de novo here. So we will get this molecular structure representation without using a database so far. This is how the method looks in detail. I will not like explain this now. I just want like to let you know this machine learning method is trained on spectral libraries. So also for the in silico methods like CSI FingerID, spectral libraries are super important. So back then when like CSI FingerID was published, it used a support vector machine for the predictions. Nowadays we use a neural network for that. And this step, so the prediction of the fingerprint, is basically run as a web service, because like the machine learning models are super huge, and so it's not so easy like to provide this for local execution. So it runs on a web service. Given our predicted fingerprint, we basically can now do the structured database search, which basically just means for each entry in our database, so we have pre-computed that already, it's also on our server. Each time you make a request, you basically say, okay, I want to search, and then you get back all the pre-computed fingerprints for your candidate list. And then you basically can match them against the predicted fingerprint. And so again, we have a score, a similarity score between the predicted and the database fingerprint, and then we can rank our structures as we would do with the cosine similarity for spectra. Hopefully the top hit is the correct molecular structure. So as a default, we usually like provide some merged biological structure database that can be used. And on this, searching in this database, we like evaluated a real world performance of like 65 to 75 correct annotations. Just to make a comment here, in our publications, we usually try to evaluate the method and not like the real world performance, and like to compare machine learning methods. You cannot just annotate any kind of data, so we do cross-validation there, and this usually, so that's why the reported numbers in the publication usually differs quite a lot. But The question is now, okay, we have searched in a database. So, and this is the same question as that has been already asked for the spectral library search. How do we know if a database hit that we have is correct? And like for spectral library search, it works quite well to say, okay, can I apply a scoring threshold? And then we had like this 0.7, and everything above 0.7 we accept, and every above below we don't accept. For FSI FingerID, this is unfortunately not working out of the box, because the scoring CSI FingerID is using to compare the molecular fingerprints is separating very, very bad. So as you see, red ones are incorrect hits, and blue ones are correct hits, and basically every kind of score can be a correct or incorrect hit. So we cannot just like over the whole data set apply this threshold and say, okay, everything about some score is correct. So we try to develop a method that helps us with that. So this is basically another machine learning model that takes different features into account and tries to judge whether annotation is a good annotation or just a wrong hit. Just to mention a few of these features, it uses, for example, score differences because between the best hit and the second best hit, and it also like searches in a more general database and looks up if there is like an even better scoring hit and all such stuff. And taking all these different features into account, we are now able to separate a lot better. So now we can clearly see, okay, if we are like above 0.7, we basically can say, okay, this is really a hit we might be able to trust. But there is one thing we have to think about for this confidence score. It is high if you like have really a high quality hit, and it is low if you have a very, very bad hit. But it might also be low if you have a super great hit, but also on the second position, another structure that is super similar. Because like this scoring really evaluates how sure can I be that the first hit is correct. And if the second one looks almost the same, then it can't be sure. So that is why you might have like correct or almost correct annotations that have a bad confidence. We will show an example in a few minutes. Yeah, but what if the correct structure is not in a database? So I think that's like the problem we always have. We search in a database, and for some of our features, we will not get a hit, or we will get a hit that makes no sense. And this is usually just because it's not in there. And like for this case, we also like have a method that at least gives you some information about your structure or about your features in your data set. And this is basically also using the molecular fingerprint, because like we have already predicted some kind of structure information, right? So we have like without searching a database, we have now substructures and functional groups, but this is usually not very informative, like to make some kind of decision, right? Or to compare your data sets or whatever. And so we developed another machine learning method that uses the predicted fingerprint and predicts compound classes from this fingerprint. And this method is called Canopus. And if you see, we now have basically a workflow from the MSM spectrum to compound classes that is completely de novo. So we will at least get some structure information for our whole data set. Yeah, a few details to Canopus. So it can predict two types of compound classes. So it predicts like around 2,500 classes from the classifier ontology, and it also predicts the NPC, so the natural product classifier classes. Again, this is a machine learning method, so that's a deep neural network now. And I just want to mention one thing that is a bit special for Canopus, because since it gets our predicted molecular fingerprint as input, we have the possibility to train Canopus on structure databases instead of spectral libraries. So that means we can predict compound classes with Canopus where we do not even have reference data for, which is, I think, a pretty cool thing. Yeah, what can we now do with these compound classes? We will probably also see that later. You can, for example, like compare two different kind of species based on their compound class distribution. So because we have annotated all our data set, we can really like nicely make statistics on that. And we can, for example, see, okay, is there a certain compound class more often in one species than in the other species? And we like could also do this for conditions, for example. So this is really like a bird's eye view on our data set, I would say. Yeah, a second thing we can obviously do with these compound classes, annotating our molecular networks. And hopefully we will then also like get some information out of that, because like then we might have a few clusters, and most of them might belong to the same compound classes, and there might be others that might be part of other compound class, and that might help us to like make better hypotheses for the propagation in the network. And yeah, again, there is some evaluation. I do not want to go into detail here, but at least we can say that like Canopus is very, very accurate. So at 782 of our like 2,500 classes, we can predict are very, very accurate, and all the others also work very great. Yeah. So that being said, I think we have everything we need like to start the hands-on part. Yeah, there is one thing left, Zodiac, but since Zodiac is like very, very memory heavy, because like it does an optimization on the whole data set, we will not be able to like compute it with our laptops, and so we like will not cover it here, but it's also like for specific cases. And if you like have some time later on, I will explain a bit about Zodiac, but for now, I think it's we are fine with that, what we have already seen. And just like this is our group. So this is currently all the people working on Sirius. And with that, I would hand over to Fleming to start the live demo. And are there already questions? No? Perfect. Ah, yeah. Okay.
Okay, I hope everybody can hear me, and also everybody can see what I'm showing right now. First, welcome also from my part. I'm Fleming Kretschmer, and I'm going to guide you a little bit through the hands-on session, or to the hands-on part of this Sirius session. First, maybe to get one idea what you might do with Sirius, or what might be a good starting point for using Sirius, is if you, for example, already have a molecular network, you can use Sirius to maybe shed some light on the parts of the molecular network that you were not able to annotate, for example, with spectral library matching. So in the next session, we are going to learn a little bit about Cytoscape and how to use it, and also how to get Sirius data into Cytoscape. This is already a network in Cytoscape where we have integrated Sirius into. I'm just going to use it for a few examples. But first, I want to show you maybe a nice file that you can look at during this presentation. There was a little bit to do for preparation. Let's just navigate to the file. So if you all have the GitHub repository for this workshop open, and if you navigate to data and then Sirius output and example, you see that there's a markdown file you can look at. And there are a few things that you optimally should have done beforehand. So, for example, you should have downloaded and also installed Sirius. There was a new version a few days ago. It is not super important that you have it, but if you have it, it's really good to have. And you should have optimally already logged in, either by using your personal account that you maybe created before, or with a workshop account. And this is what I'm going to show you now. So this just linked also on our homepage. I hope it loads. Let's get into Sirius and see how it would look like if you just open up. So this is the pretty much empty Sirius interface. You don't see a lot, but what is important here? Maybe what was the command for hiding the zoom bar? Okay, that's not. Maybe I have to.
So the endless switch on that one.
It's not working, but it's not super important. It's also okay. Let's just do it. I mean, you can see, yeah, especially if I just make the window a little bit smaller, you should be able to see everything.
Definitely decrease like take the minus on the filters on the zoom on the right.
Yeah, of course. Yeah, sorry. Yeah, at least, yeah, now we can see a little bit more. And unfortunately, our homepage is not loading right now, but we still have time to maybe give you a quick tour on the main buttons you see in Sirius. So here in the toolbar, you have on the left, at the top, you have all the buttons for opening and saving files, and also opening and saving projects. We'll soon see what the difference is between importing and loading. Here you have all your buttons related to computation. Also, what we are going to look at in an example pretty soon is how to use custom databases. So this button is for the custom databases. Here you have a button for showing running jobs. And what I actually wanted to show you, and now we can even log in. Here in the right, you have settings and log. Also, you have a link to our documentation where you can maybe look at. But what I wanted to show you is to log in. So if you click on here and click on account, maybe the best thing to do would be just to log in with the workshop credentials. And these are on this page, which is linked in the GitHub Markdown. So let's all use this account to log in. Let's copy the email, the password. Yeah, it's if you have the GitHub page, and there's a link provided. So this was the GitHub. And if you are in the correct folder, so if you are in data series output example, there in the preparation section, you have a link for bio.informatik.uni Jena. And there, if you click it, you have the credentials for the workshop login. But also, if you have maybe already made your own account, you can also use this to log in. Okay, now let's click on login and hope it works. Okay, now we are logged in. And you can see that now this web service button, maybe you noticed it before, it has a green tick now. And if you click on it, it's always a good thing, especially if you see that maybe Sirius is not doing something. Yeah. Yeah, yeah, of course. Is anybody else having trouble logging in?
Who is logged in? By raise of hands.
Ah, that's, yeah, That's a good share. Okay. Cool. So if you're logged in, you can see this this little pop-up, and you can see that everything seems to be working, which, as Markus has mentioned, some of the features in Sirius need an online connection, so it is important that you are logged in and everybody also has a connection to the servers. Okay, so we still have an empty project space. Let's look at some data. And to import data, you can either use the import button up here, or, which is maybe more easy, you can simply drag and drop some files. So I hope everybody has also downloaded the GitHub repository and the example workspaces which we provided. For this first part of the hands-on session, we're just going to import the data that we created yesterday using mzmine. So we are going to import a file that was already pre-processed. It's also possible with Sirius to just drag in your mzml files, so your raw files. Yeah, but for this part, we are going to use the mzmine file. So the mzmine file in the GitHub repository, it's located in the data subfolder, and then in Sirius output. Sorry, not Sirius output, of course, but mzmine outputs, the mzmine file. And then for this part, for this hands-on session, we are all going to use the example data. So not the group data, but the example data. So we go to the example folder, and now we should see all these files. And what we are going to use is the example _Sirius.mgf. So does everybody have the folder open and see these files? So just again, it's in the workshop repository, and then in data, mzmine output, and example. And from the, you have to download the file from the repository, or maybe for this part, it would also be enough to only download this MGF file. Or maybe it's not super important. Maybe if you have another MGF file lying around, for this part, it would also be all right to just use this. So I hope everybody has some MGF file, and we are just going to use this MGF file and drag it into Sirius. Now we can see that it's loading, it's importing, and we have this MGF file is quite large, so it's going to take a little bit of time, not super long, but maybe while we are loading, we can look at the contents of this file. So it's always, also Daniel touched on it a little bit, it's always a good thing to look into your data. So especially if you see that something is not working when importing, it's a good thing to just open up your data in some kind of text editor and see that the file is not empty and that everything you want there to be is also present. So for example, let's get back to this MGF file. You don't have to open it right now. I'm just going to show you. This, I hope you can see it a little bit. This MGF file that seems to be all right. You seem to have all your peaks. You seem to have a line which says MS level 1. And also, if you scroll down, MS level 2 somewhere. So this file seems to be all right. But that's not the important part. I hope that everybody has now some kind of data in Sirius. So maybe raise your hand if you have data opened up in your Sirius. So you have something in your compound list. Okay. And the other people, what is the problem? Or are you still opening data? Ah, okay, it's still open. That's okay. It's just a very big file. It will take a bit, but soon you will see something, and maybe I can then explain what you have now in your view. So at the left, you now have a compound list. You have the list of all the features that are in your MGF file, and you can scroll down through this list and see that it is quite big. Here at the bottom, you can see that it's about, maybe now I'm going to make Sirius big. You have about 6,000 files. So this is also why it's taking so long, or not files, but 6,000 features here. And you have various things to look at. When you click on a feature, you can see the feature name in the top of this entry. So this is example Sirius 204. You can see the ionization, the precursor mass, the retention time, and also once you have run some kind of computations, you can see the confidence score that Markus already talked about. But right now we don't see much else. So we have our compound list, we can look at our spectrum, and maybe if we just scroll through these compounds, here you can see some blue peaks, for example, which means that these are part of the isotope pattern which is detected, but nothing much else to see here. So let's do some computations. And for this, you have to know that you can easily select multiple compounds. So just click on one compound in your list and then hold Shift. So pretty similar to just your standard file manager, you can hit Shift and click on another compound to select a range of compounds. So now you've selected 4 compounds, and I hope everybody now has something open in Sirius. Okay. And when you have selected some compounds, just hit right-click. Now you have a right-click menu where you can do various things. And for this, we are going to go to the compute feature here. So right-click on just a set of compounds and hit compute. So now I will wait a bit if someone has problems. Of course, yeah. Yeah, so the question was, if you don't use preprocessed files, for example, from MZMine, but just drop in your MZML files, what is Sirius going to do? It will look a little bit different. You can also just drag and drop your files, but it will give you a few other options. For example, it will ask you to align your files during import. This is just one dialog box which is going to open up. And also, maybe I can close this window. Here you have an LCMS tab, and if you import raw data, there's a quality view where you can look at your LCMS data, for example, the chromatographic peaks and stuff like that. This we are not going to see when we use already preprocessed data. Yeah, but you don't have to set many things when you import raw data. Okay, let's get back to the compute option. So still select a few compounds, right-click and compute. And now I'm going to walk you through this window, which you are probably going to see quite often when you're using Sirius. Here you have all the various tools that Markus introduced. So you can see these big buttons. You have a button for Sirius, so for the molecular formula identification, for the mass decomposition part. You have Zodiac, which we didn't touch, which we didn't explain before, which we are also not going to use here right now. You have 2 options for CSI FingerID, and then in the end you have Canopus. So let's go through all these features. Sirius, you probably want to turn on pretty much all the time when you're doing any kind of computation. So this is pretty much the basis for all other tools. Now you can see there's quite a lot of options, but not all of them you really have to set or change. And I'm also not going to explain all the options. One thing that is good to know is that for most options, you can just hover over the settings and get a little tooltip that gives you a little bit of information. And of course, you can also refer to the documentation if you want to know more about a particular setting. But this right part here for Sirius, we are not going to change right now. One important setting that you should make is just pretty much the first setting where you set your instrument, and you should just set it to the one that closest, that matches most closely what you've actually measured your data with. So for example, we could set this to Orbitrap, and this is kind of a profile. So for example, now that I've changed it to Orbitrap, also another setting changed. Now here in the MS2 mass accuracy setting, we have 5 instead of 10, which was the default before. Yeah, but this setting, the mass accuracy is also important to set. Yeah, I think the other settings I'm not going to go into right now, maybe just one setting. You've already heard from Markus that many different molecular formula candidates are computed and they are compared against each other. And this setting pretty much tells Sirius how many molecular formula candidates it is going to store and is going to show you. So we are going to see soon that we are displayed, in this case, about 10 molecular formula candidates. But we are not going to change this right now. Another setting that is or can be important, depending on which data you have, is this elements allowed in molecular formula part. So here you have this section where you can actually set all the elements that can be part of your molecular formula. For many cases, you do not have to change these settings. For example, for many elements, there's an auto detection. So for example, for bromide, there's an auto detection toggled on. You can see bromide, and these fields are grayed out. If you would deselect this option, you can actually set the number of bromide atoms which are allowed in your molecular formula candidates. But for the most part, the best option is to just keep it on the auto setting. So it's going to auto detect the elements. For some elements, this is unfortunately not available yet. So for example, for fluorine and for iodine, so the last two elements, we don't have the auto setting yet. So if you expect that fluorine or iodine is in your data, you should set the slider, for example, to this. One thing to keep in mind is that, of course, you could theoretically also change the slider to infinity or to a very large setting. But increasing this slider will also increase your runtime. So for these settings, you should always choose reasonable values. So probably you will not expect a molecular formula that contains 15 fluorine atoms. But let's just keep it off for now. Here you also have a setting to select extra elements which are not in the list. But we are also not going to use this now. Zodiac, Markus already mentioned that it needs quite a bit of memory. And it's also, for example, now we have only selected 4 compounds. That is mostly useful if we have a really large set of compounds, and especially if we have it from the same sample. So we are not going to use this now. Instead, we are going to the predict fingerprints section from CSI FingerID. So let's toggle this on. And one setting you have here is to use fallback adducts. So remember, we imported the file from mzmine that we created yesterday, or that was in the GitHub repository. And mzmine already has adduct detection, and Sirius also has another adduct detection. But maybe in both cases, the adduct detection failed. And in these cases, we can use fallback adducts. So for example, maybe we can toggle this setting here to also cover intrinsically charged compounds where we didn't get the auto detection of adducts right. Also, there's an enforced setting. So maybe even if you have the automatic adduct detection, you might still want to use these adducts that you selected here as fallback, so they will still be considered for this part of the computation. Also, maybe one thing that Markus made clear is that you can use Sirius or this Sirius software for completely de novo annotations. And this is also shown pretty nicely here in this computation window. So if you only toggle options on the left side, so for example, Sirius, Zodiac, predict fingerprints, and Canopus, let's just close this box here, you would be on the total de novo workflow. But another thing that we also want to show you today is how to do structure search. So this is not de novo. So let's toggle on this option from CSI FingerID. First, this was the fingerprint prediction setting, but now we want to actually search in a structured database. And here you get a setting of various databases that are included in Sirius where you can search. So for example, you have the bio database that is toggled on by default. And if you scroll down, you have various other databases. And if you have created a custom database, which we are going to do later, you will also see your custom database here. And one thing to keep in mind is that, of course, maybe you would be tempted to just search in all databases. And maybe it is, or it's probably more likely that your correct structure is in any of these big databases. But if you select all the databases, the ranking part of Sirius or the ranking part of CSI FingerID is also going to become harder. So I think this was also part of a talk on Monday. It is always a good idea to select a database that most fits your samples. For example, if you're looking at human metabolites, a good setting here would be to use the HMDB. If I can find it, here it is. Yeah. Okay, and this part, I think Markus mentioned it just briefly. We also have this tool Algordo for lipid class prediction. And this setting, you really don't have to touch. It's just, you will see an additional view or additional help for lipids that may be detected in your sample. But we're not going to use this option here, or we're not going to change it. Okay, now we have set all your settings, and maybe for some tasks you want to do recomputations. So maybe you do computations, and then you find out later that you should have maybe changed one setting. And this you can do if you have made your computations and do other computations. You should hit this option, recompute already computed tasks. And this is also a little bit smart. So for example, if you have done Sirius and you have done predict fingerprints, and maybe you only want to change settings for the database search, you do not have to run Sirius for molecular formula identification again, because you already did it. Okay. Another thing to show here is the show command option. So maybe you have just spent a lot of time and fiddled around with all these settings and got some good settings. Here we can show the command, so all the settings that you have made. And maybe you want to run Sirius on a cluster, for example, if it's taking too long. And then you can just copy this command to use it, for example, in the Sirius CLI version. Okay, and I hope everybody has now the compute dialog and has made some settings. It doesn't really matter for this part, but you should have turned on some options. And then you should hit compute. So we're actually going to do some computations right now. Please do not use the compute all button right now, because computing everything is going to take a long time. Just select a few compounds and hit compute. Okay, just because we have toggled the recompute option, we actually haven't computed anything, but because we have this option, we are going to, we are shown a warning, but let's just click on yes. It's submitting, and you can see here in this jobs window, some things are running. You can also see in the left, in the compounds view, that there are some gears, but apparently it's already finished. So what you can see, I'm already in the, I'm still in the LCMS tab, which I'm not going to have for this example. Here you can now see that you have a setting for confidence. Oh yeah, maybe it's a good idea to ask if everybody has something. So I hope everybody could run some computations. And if you run computations, for example, on 5 compounds or so, maybe a few of these compounds now have an additional entry for confidence score. Yes?
I think we may be crashing the server as well.
Oh.
We got disconnected.
Ah, okay.
Sorry?
Are you logged into the workshop account or to your own account? Ah, okay, maybe it would be a good idea to switch, because there are actually different servers for the workshop accounts, which might be faster. Yeah, exactly. Okay, but it's also not super bad if you don't have anything, because in a few seconds, I'm going to load an already pre-computed workspace, a project space, sorry, and we are going to look at some examples in more detail. But just one thing to show, now we have some computations and we have some confidence scores for these computations. You can already see something. But again, now we're going to load something new. We are going to load all the results. One thing that I haven't shown you is that here in the top bar of Sirius, you see your Sirius version, but you also see the project space which you are working on right now. So even if you just open up Sirius in an empty project, you will be on some kind of project space here in a temporary directory. And if you close it, it would be saved, but only to this temporary location. So a good idea is to just right now save our project space. So just click on the Save As button in the top bar and just create some folder. Let's just call it test. And then click on Save As. It's also going to take a little bit of time, but now we saved it. And now you will see that in the top bar, we're actually now in this test project space. And if we would close Sirius, it would save all the things that we've done. So probably in most cases, you will not lose anything if you just close Sirius. Okay, now we have saved it. And what we are actually going to do is load our pre-computed project space. So I hope everybody has downloaded the zip files we provided of the project spaces. So again, if you are in the Markdown, you will see this link, download and extract the Sirius example workspace. So it's important that you not only downloaded it, but also extracted it to open it up in Sirius. I hope everybody has an example workspace. Is there someone which does not have this workspace? Okay. Oh, the file, the link. Ah, okay. So let's just maybe show this. So if you're saving your project space, maybe the best thing is just to click on new folder here in the top bar. So on this button, create new folder, and just give it some name. Now we have test 2. Okay, and just click on save as. So we changed our project to this location. Okay, but now let's finally open up our example project space, which you should have somewhere on your disk. So for me, I just put it in the documents workshop folder. You should have a folder named example Sirius project space structure. Does everybody see this folder? Has everybody downloaded it? You can't access the file? Okay, because it should also be in the Google Drive. So let me just see where it is. So you weren't able to extract it. It would show some error. Okay.
So we are working on that example.
Yeah. Just unfortunately I do not know what to do when the extraction fails. It should work. Maybe you should use another program. Okay. Okay. Just to see, just to show where it is in the participants folder of the summer school Google Drive. You have a Sirius folder, and there you have this example Sirius project space structure.zip. And this is the file that you should download and also extract. So how many of you have in project space downloaded? Okay, so yeah, it's quite a big project space. Google Drive or the other link? Maybe try the other link. So the other link, just to show it real quick, it was in the GitHub repository. So if you access the CD, MRG, and so on, the GitHub repository, and navigate to data series output example, you will see various links, and also you will see one link for the example project space. And this one is not working. You want? USB drive. Yeah.
Does it matter if it's computer ready?
Sorry?
So if the series already computed some of the chronicles that I need to...
Yeah, you should use it so we can look at the same examples. But maybe if it's not working for many people, maybe we can just skip this and I will show you examples. And if you have computed a few compounds, then you can also look at these and you will see similar things at least. Yeah. So let's just look at a few examples, and if you have something computed, you can maybe follow along. And otherwise, if you have at least computed like one compound, you can also just go through the views. Might be the best idea. Okay, so but I'm going to open up the project space. So for those of you that have the project space, just click on Open, navigate to the project space. Okay. Apparently, the download link for the project space is working again. So if some of you want to try again. But yeah, let's just open up the project space now. Click on Open. You can also drag and drop it in if you have the folder. It's also going to take a little bit of time, but shouldn't take too long. Okay, now that I've loaded in, we should have computations for all these compounds here. So if you scroll through the list, you will see that many of the compounds have a confidence score. And as Marcus already explained, this is how sure the software is that the top structure hit that we got is actually correct. And because we still have really many examples here, one thing we might want to try, especially if we know what we're looking for, is to use the filter option. So here in the top bar, you can either do a text search. So if you have a specific feature ID that you're looking for, you can type it in here. But you also have some more advanced filtering options. So in the, just to mention it quick, besides the search bar, you have these three dots and you can click on them. And then you have another window where you can change various things and, for example, filter by MZ or filter by retention time or even by confidence score. So just to show you how you would do this, you could, for example, only want to show all the compounds that are between 200 and 210 MZ. So you would just make these settings here. And then you would click on Apply. And if it worked, you would see that you now you now have filtered down your compound view to only these compounds that are between 200 and 210 MZ. Yeah.
What's a good Sirius score?
For the confidence? Yeah. This is a good question. Maybe let's just reset the filter so we see everything. So for resetting, you would click the filter option and then click on Reset and on Apply. So now we have our whole compound list. And one thing you can do is right-click somewhere here and click on Order by Confidence. Now you see that all the compounds with high confidence score are at the top. And of course, there's no one value that fits everything. But often it's a good idea that if you have above 0.65 confidence score, that the annotation should be quite good. But of course, it's always good to look at various views and various scores that you have. You mean the filtering part or the sorting part? Yeah, sorting is just, if you have your compound view on the left, you just right-click somewhere here. You have this menu where we also did the computations, and you can make summaries, for example. But here you have options to order. So you can order, for example, by retention time, by mass, by name, but also by confidence. And if we order by confidence, we will get all the hits at the top that have the highest confidence score. And especially if you have a very large project space, it might be a good idea to first look at the hits where we have good annotations, and then later on look at the hits where we do not have, according to the confidence score, that good annotations. But let's finally go into one example. And you don't have to follow along for this part. I'm just going to go into the molecular network and just grab some cluster where we, at least in this network, do not have spectral database find. So let's, for example, look at this cluster here. You can see if you zoom in, or I can see at least, that we have already annotated our network with a few things, which you're going to learn in the next session today. For this example, I'm just going to grab one node here. Here's a node that is connected to piperine. I'm just going to select it and get the feature ID. So this is not important for the following along part. The only thing that is important is that you should go to Sirius and then type something here in the search bar, because now we're looking for the feature 9065. So this is also in the markdown file. If you still have it open, you can just copy and paste this 9065 into the search bar and then click on enter. And now you should have only one compound showing in your compounds view, which is this particular feature. If you do not have anything, the reason might be that you still have a filter on. So if these 3 dots are still blue, you should click on them. So you are now in the filter menu, and you can click on reset and on apply to reset your filter. Because we do not want to filter by MZ for this part, we only want to filter by this feature ID, by this 9065, which we just got out of Cytoscape. Okay, let's just go through these views. So it is not important that everybody has exactly the same example. I'm going to show a few things, but if you have some other computations that were finished, you can also click on them and go through the views. So the first thing you're going to see is this formulas tab. If you do not have it open, just click here on formulas. And this is an overview on the mass decomposition part. So the first part of the Sirius tool chain. You will see here a list of the molecular formula candidates that you have computed. And you will see various scores for each formula candidate. Marcus already explained a little bit. For example, for this first molecular formula candidate, we have a Sirius score of 100%. So this is pretty much the optimal value here. And you also have isotope scores for matching the isotope pattern. You have tree scores for the fragmentation tree, which you can see in the bottom right. So this is the fragmentation tree view. You also can look at the number of explained peaks. So in this bottom left part where you can see the spectrum, using the mode drop-down menu, you can navigate to MS2 to show the MS2 spectrum. And if you do this, you will see that you have peaks probably in various colors. For this example, because we have explained many peaks by the fragmentation tree, all these peaks are highlighted in green. So a green peak in this view just means that we have annotated, or that this particular peak can be explained by the fragmentation tree for the molecular formula candidate that we selected. So for the first molecular formula candidate, can pretty much explain all the peaks in the MS2 spectrum. Also, a good thing that you can do, you can click on these peaks. For example, you can click on this small peak here, and you will see then that this node in the fragmentation tree highlighted. So these two views are actually synchronized. If you click on something in the fragmentation tree, the corresponding peak in the spectrum view will actually light up, so it will turn blue. And yeah, the other case around also works. If you click on a peak, you can see the node in the fragmentation tree that is associated with it. Yeah, question?
I happen to click on a molecule that has 6 out of 5 explained peaks. What does that mean?
Oh, that should not be the case. That's strange.
Maybe because of stopped computing.
Yeah, one thing here is that actually the explained peaks, if you would count in the MS2 spectrum, this explained peak score, that it doesn't count the precursor, but the precursor should also not be part of this. So you shouldn't have 6 out of 5. There must be some kind of bug. Yeah, another question?
So this one's got a problem Sirius score of 99.999%.
Yeah.
But then 8 out of 10 explained peaks.
Yeah.
So how is that? I'd expect like, I don't know, 10 out of 10.
Ah, yeah. Yeah, it really depends on the spectrum you have. I think it's not super likely that you will explain all the peaks. So you might just have some noise peaks or some peaks that we do not know what to do with. So it's important to always use the different scores. So the Sirius score in many cases, it is really high. So it's not uncommon that you, for example, have only one molecular formula that has a score of 100% or 99.9%. And you can even have this if you have only a few peaks explained. Yeah. So for everything here, it is the case that you should look at multiple values to see if you trust the molecular formula annotation. Another question, yeah. The adducts you can see here in the for the molecular formula candidates. What do you mean? Yeah, you would for this example, we only have the M plus H plus adduct, but if you had another adduct detected, it would also show there. Yeah. So for this, it's pretty boring this because we have the same adduct for all the molecular formula candidates. Because we have the lunch break coming pretty soon, and we are not going to extend into the lunch break much. I'm just going to show you a few quick things.
I think we should like go into lunch break now and proceed with the other things after the lunch break. So in the hand-on session later after the cytoscape part, because like then we can also fix the missing downloaded workspaces and stuff in between.
Okay, so then let's stop, and maybe everybody that wasn't able to download the workspace, maybe try again so that we have some examples to look at later on.
Open the drive. Participants folder.
Archive in Windows.